In this video, we're discussing use of vector instructions, or also called single instruction multiple data, or SIMD. So the purpose of SIMD instructions is to allow you to do more work in fewer cycles. So if you think about regular operations, regular CPU instructions, we call those scalar operations. At least in a SIMD context. Scalar operations work on a couple of values at a time. In this case, we're adding two values from two arrays, A and B at index I, adding that up and getting the sum. This would take, well, I suppose, probably two moves, one add, and then we have our sum in a register. And with SIMD processing, it's the same number of instructions. We've got a move to load an array of, in this case, 8 elements into one register. Another move to load the other array of 8 elements into a register. And then an add, which computes an array sum of all of the separate elements in this array. And that ends up in a register. So it's much like normal instructions, except they all operate on arrays of values as opposed to individual values. These arrays is what they also call vectors. Right? It's called vector instructions for some reasons. For some reason, I think it's a little confusing, but there you go. So the Intel CPUs, they have large number of different vector extensions, starting out with something called MMXx back in the day, and then SSE, and then now it's AVXx, and each of these have several different versions and flavors to them. I think the main thing to know about these days is AVX, which is the XMM 128-bit registers. And then you have your AVX2 YMM registers, which are 256 bits, and now relatively recently AVX512, which is ZMM registers. They're 512-bit values. So yeah, it's important to note that 512-bit ZMM register, the lower 256 bits of that is the YMM register. So if you modify your YMM 0, you end up actually modifying your ZMM 0 as well, the lower 256 bits of it. So we can treat these wide registers as different kinds of arrays, depending on what operation we're interested in. So you could think of a ZMM register as an array of 64 8-bit values, right? A uint 64, or 32 16-bit values, or 16 32-bit values, or finally 8 64-bit values. We use different instructions to operate on these registers as if they are these different kinds of arrays. So here's an example. VP add USB is the example from here. It's a vector parallel add unsigned byte. Right, so the B at the end here says the size of the individual elements. So that's kind of understood. You have byte elements, that means there's 64 in total in one ZMM register. The naming of these instructions is not all that consistent on Intel. Usually the ZMM with the AVX512 instructions, they start with VP, and the AVX2 instructions, they start with a P, and I forget what the ones for XMM are called. Right, so yeah, it's a little tricky to kind of find the right instructions because there's really a large number of instructions in this instruction set, because of all the various sizes involved. both the size of the registers and the size of the internal fields or elements that we're interested in. So this VP add USB, it performs essentially this loop. This is a scalar expression of the loop. 64 times around the loop, add up the individual elements. Right? So one instruction performs that entire thing, and just like in any other add or standard ALU operation, it takes one cycle. So here we've got 64 add operations in one cycle. This is the Intel SIMD instruction set sort of evolution, starting with MMX, with the Pentium 2 back in '97. They've added on gradually all these various extensions. It's a little unclear how they decided on what instructions to add. My hypothesis is that it had to do with specific applications that some big customers were interested in. Perhaps some supercomputer applications really needed some specific instructions that would speed up whatever simulations they're running. Perhaps some benchmark programs like the SPECflop or SPECint benchmarks could really benefit from some specific instructions, and they ended up sort of gradually adding on more and more functionality, unfortunately with not that much principle to it. I'd say by AVX 5.12 it's starting to look somewhat principled. Like there's a pretty clean interface, but steps along the way were kind of messy, as you'll find out when you look through the instruction set for the various size registers. So what are some strengths and weaknesses? It's really nice to be able to do 64 times the work, right, with no extra instructions. This, yeah, almost all the vector instructions are as fast as scalar instructions. So you really get a 64 times speedup if you're using 8-bit elements in your vector registers. Unfortunately, most of these operations are only vertical, in the sense that they only operate on independent elements or columns. They don't operate across the array. So you can get a sum between two vectors, just like the VP add, but you might not be able to get a sum, the sum of all the elements in the vector. And generally speaking, where there are horizontal operations, they tend to be slower, and they're quite limited. There's a number of different operations for shuffling the elements, reordering the elements within register. Shuff, perm, blend, and align are some. They all do different variations of reordering registers. But it's pretty confusing, and they're rather limited. Although I should say in AVX 5.12 there appears to be a full shuffle in, or is it a full permutation at least, inside for ZMM registers. So we're getting there. So that basically means you can reorder them in any order you want, all the 64 elements. Yeah, so maybe the main weakness, or on the okay side here, is that it's pretty confusing. It's a little messy. That doesn't matter so much when you're using the C compiler to auto-vectorize the code for you, although it does seem to get confused from time to time as well. On the bad end, it's really only useful for mass processing data that's sitting around in rather densely packed arrays. You don't get much benefit out of it if you only want to read 1 byte from each cache line, let's say. You don't get any benefit if you want to chase a lot of pointers. You can't dereference pointers in these vectors. There's some inefficiencies in combining vector and scalar code, so switching between the two, moving a value from a ZMM register into an RAX, let's say, that can have some penalties associated. It's only a couple of cycles, but still. And there's extremely poor portability. If you compile your program for a certain architecture or a set of extensions, it basically can't run on other CPUs. I suppose if we follow this, look at this diagram, if you compile it for a Prescott, it's going to run on a Haswell. But if you compile it for a Haswell, it is going to crash on a Prescott. So they keep piling them on, more or less. Although look at this here. Xeon Phi has this ERCD, while Skylake has this other one, DQBWVL. There may not be, like this may not have all the instructions that is in this set. Last I heard, Intel decided to shut down Xeon Phi. This was an intended competitor for the GPU model. Lots and lots, of course. I don't think it went anywhere. Okay, so how do we use this? Certainly the easiest way is to use the auto-vectorizer in the C compiler. So just supply -03, which we usually do anyway, and the C compiler will do its best to use vector instructions when appropriate. If you don't want it, you can disable it with this flag, or for individual functions, you can also specify that you don't want this function to be vectorized, but you can't do it for internal blocks within a function. If you want to handwrite some vector code, the easier way to do it usually is to use what's called intrinsics. These are wrapper functions for all of the available instructions. There's a very good guide here. We will take a quick look maybe. We can do that. Looks like this. It's not really a guide, we call it a guide, but it's a reference. So here we've got all of the instructions available, and you can specify which architecture you're working on and so on. It's quite helpful, and if you click on it, you can also see the exact instruction that it translates to. So here's the function name and then some parameters. Right, lots of new data types, 512-bit integer register, 16-bit mask, this sort of thing. Okay, so the intrinsics are helpful. There's some getting used to, all the new types and the very long function names. But it's nice to have the compiler help you out a little bit. And it generally generates efficient code. It doesn't necessarily generate what you told it to, but it'll be close. Sometimes just using plain assembly, inline assembly will be cleaner. You get even tighter control. If you look at the generated assembly from the intrinsics and you see it doesn't do what you thought it would, then it probably would be worth going to inline assembly. The syntax can be a little bit of a mess, especially for the new mask register instructions. Right, so here in the constraints, you use an X to specify a vector register. And there's some flavors to get the ZMM versus the YMM versus the XMM registers. You have to look that up. Right. It's not clear that the auto-vectorizer is going to do what you want it to do. It'll generally generate correct code, not always very efficient code. It's a good idea for any tight loops. Any place where you're really spending a lot of time and it's relatively short, to take a look at the assembly and try to understand what it's actually doing, because oftentimes it'll be somewhat inefficient. So it's always a good idea to use the auto-vectorizer first. Writing vector code is a pain, and it can take quite a while, and then it'll be, when you want to change your code, now you're kind of stuck having to rewrite this vector intrinsic code as opposed to standard easy scalar code. So try to use the auto-vectorizer first. Most of the time, don't even bother with looking at what it did. It'll be fine. It's just for places where you have a tight inner loop, where this is the key logic of a big, what are we doing? Maybe we're writing a sort program, right? We're wanting to sort this very large file, and we want to try using vector instructions. All of the file is going through a small loop. Inside of that loop, let's see if the compiler actually did vectorize. You had some idea that this could be vectorized. It's not clear that the compiler would do it. Take a look at it, see if it generated something efficient. If it didn't, then maybe give it a shot to use intrinsics instead. Okay, so how can we help the auto-vectorizer to actually generate vector code? You certainly want to use arrays for all your data. We don't want any pointers anywhere really in the data, or if you have any pointers, keep them very uncommon. You want to keep them as tightly packed as you can, the data. Oftentimes performance is limited by memory accesses as opposed to arithmetic. So you want to make sure it's compact so that your memory bandwidth is conserved. It's not just a question of using a lot of memory, it's memory bandwidth as well, right? This is especially true for vector instructions. They are limited by the same memory bandwidth, but they have up to 64 times the arithmetic bandwidth, or ALU bandwidth. So you'll quickly run into memory bottleneck. You want to avoid referring to the same data in different ways. In particular, if you have data that you're treating as, say, 64-bit integers, don't treat it sometimes as a character array, right? Don't switch between types. If you do, the auto-vectorizer has a harder time keeping track of what code is changing, what values, and will avoid doing parallel execution or vector execution in this case. We'll have a hard time reordering operations and so on. And also, inside of your loops where performance is important, avoid function calls. Compiler oftentimes doesn't know what the function will do and will have to be conservative about the order of operations. Avoid accessing volatile variables and compiler fences in general. So a function call is sort of an implicit compiler fence for most functions. But you can also have an explicit compiler fence, right, with the asm volatile. Yeah, I'll just write it here. Right, so this is the explicit compiler fence. There's some nice shorthand for it, I forget. Compiler fences can be very handy in performance debugging. You don't want it, I mean, unless you need it in order to preserve correct execution, like to prevent ordering on purpose. You don't want it in your final code. But for performance debugging, performance diagnostics, a compiler fence can be very handy to force the compiler to do what you wanted it to do. So this tells the compiler that changes, there may be changes inside of this instruction. Right? Parts of memory may change. So you can't rely on whatever you loaded from memory over here to be the same over here. And you can't really reorder instructions across this fence. Very handy. It doesn't generate any assembly. It just tells the compiler what's allowed, basically. Right. Oh yes, and don't forget to specify either the specific architecture or which extensions you want the compiler to use when generating the vectorized code. Some handy instructions you might want to look at, or names, sort of rough names when you're using that reference, Intel's vector reference. Blend is for mixing values from two different registers. It's also called mask move in the newer instruction sets. Align is for picking one part from one register. Let's see. No, you concatenate two registers and then you rotate, and you get whatever's you get some combination of two registers. Some rotated concatenation of two registers. Shuffle reorders within one register, elements within the register. It's a limited permutation. There's only some things it can do. I think it had to do with efficiency of the implementation, perhaps. Permute is more complete. There's actually a complete permutation, so you can say exactly which order you want them in. There may be a performance there. Generally speaking, any horizontal operations that span the whole array, not just 128, but maybe 512 even, would end up taking perhaps 3 cycles instead of 1. So try to focus on vertical operations for anything inside of your loops. Right, that's all we've got for vector instructions today. Thank you.